Hello to everyone. My name is Marco Cafiso. I am a second-year PhD student in physics at the University of Pisa. And today I want to talk about this project named Temporal Complexity of a Bio-inspired Neural Network. This project is done in collaboration with my supervisor, the Dr. Paolo Paradisi of the Institute of Information Science and Technologies of the CNR. The idea behind this project is to study a very simple bio-inspired artificial neural network without learning algorithm with some tools that comes from the temporal complexity theory to show if these systems displaying some complex intermittency. The model that we chose is a bio-inspired variation of the Hopfield model, so a model in which each neuron can have only two states, 0 and 1. And the dynamics of each neuron depends on three main rules. The first rule is the refractory period rule. So a neuron that passes from an activate state to a deactivate one must remain deactivate for at least TREF consecutive time steps. The second rule is the maximum firing duration rule that says that a neuron cannot fire for more than Tmax consecutive time steps. And finally, if neither rule 1 or 2 are applied, the dynamics of the neuron follow the classic Hopfield dynamics, in which the postsynaptic neuron, the state of the postsynaptic neuron depends on the presynaptic contribution. If the contribution is greater or equal than a threshold, the postsynaptic neuron fires. Otherwise, the postsynaptic neuron can fire with an endogenous firing probability equal to P endo. For the data analysis, we use the so-called EDIS algorithm that starts by computing the diffusion variable, that is the integral of a random walk generated by applying some specific walking rule, in this case the asymmetric jump walking rule, to the neural coincident event in the sequence. A neural coincident event is defined as the event when we have more than n neurons that fire simultaneously in our network. After the computation of the diffusion variable, we apply to that the determinant fluctuation analysis and the diffusion entropy analysis to estimate the Hall's coefficient H and the self-similarity index delta. There are two important indexes that allow us to tell something about the temporal complexity of this model. We decided to study this model with two types of connectivity between neurons, the scale-free connectivity and the random connectivity. So we decided to develop a scale-free network, a Erdos-Renyi network, by applying some specific degree distribution. After that, we performed different simulations by varying the parameter of the model, and we found a large variety of dynamical behaviors that we decided to classify them in a qualitative way by looking at the shape of the total activity distribution. After that, we decided to focus our attention in these cases that I report in this slide, in this poster. In particular, in the power law cases that are found in both types of networks, in the same range of parameters, but with different endogenous firing probability. After the data analysis, we can say that the Hall's coefficient have two main trends. In particular, in the short time regimes of time lags, we found an Hall's coefficient that is always less than 0.5. So we have a sub-diffusive behavior that is related with a strong anti-correlation in the diffusion variable. While in the long time regimes of time lags, we found a Hall's coefficient always greater than 1. So we have a super diffusive behavior that is related with a strong correlation in the diffusion variable. With the diffusion entropy, we found a self-similarity index that is always lower than 0.5, and it confirms the sub-diffusive behavior of the diffusion variable. So to conclude this presentation, with this preliminary work, we want to demonstrate that even if we used a very simple spiking model, by varying some parameter, we found a large variety of dynamical behaviors that can be studied with the tools that comes from the temporal complexity theory. And if you want to investigate more this work, I put that on the archive. And after this, I want to thank you for the attention.